Thanks, Abhi, for that introduction. So the subject of this work is outsourced databases. With the rise of cloud hosting and software as a service platforms, outsourcing of sensitive databases is becoming increasingly common. Outsourcing has many advantages, but one major disadvantage, which is security. If the party hosting the database is malicious or gets compromised, sensitive information can be stolen. Unfortunately, such breaches happen all the time, so we would like to protect the data even in the event of a breach. One widely proposed solution for this problem is for the data owner to encrypt the data before it's outsourced with a key known only to them. This protects the breach from exposing sensitive data, but also prevents anyone from making database queries and retrieving records. By design, encryption destroys the functionality of the data. Recently, encrypted databases have been suggested as a way to resolve this tension between security and utility. The data is encrypted with a key known only to the data owner, but can be queried efficiently with that key. Encrypted databases are an active area of study for academics and have been deployed in practice. Generic techniques for building these systems, such as ORAM and private information retrieval, are too slow. So to make encrypted databases efficient, people have proposed using schemes that leak a little bit of information about the data. The exact leakage varies from system and scheme to scheme, but one leakage that's in common to all these systems is the access pattern leakage, which means that the adversary can see the set of matching database records for every query that's made. To understand the security that encrypted databases can achieve, therefore, the crucial question is, what can an attacker learn from this access pattern leakage? Surprisingly, recent work by Kellaris et al., Lacharité et al., and Korneropoulos et al. Earlier in this session has shown that in some settings, the access pattern leakage by itself is sufficient to reconstruct the data. This is called a database reconstruction attack, or DR for short. While very good and interesting work, this prior work has some shortcomings. It requires a lot of queries. For example, Kellaris et al. Would require 10 to the 26th range queries to attack salaries. It requires strong assumptions about the data. For example, Lacharité et al. Requires the database to be dense or to have every single possible plaintext value occur at least once, and only holds for specific query types. For example, Korneropoulos et al. Only target k-nearest neighbor queries. And it seems difficult or impossible to remove these restrictions using the techniques of these authors. So to get attacks that use fewer queries, make weaker assumptions, and maybe even work for any query type, some new ideas are needed. The meta contribution of this work is the insight that access pattern information is a binary classification in the machine learning sense. With this, we develop a correspondence between ideas from statistical learning theory, such as VC dimension and pack learning, and leakage from encrypted databases. We use these ideas in two ways. First, we present 3 new database reconstruction attacks on access pattern leakage from range queries. These attacks generalize and improve prior work on range queries by Kellaris et al. And Lacharité et al. For real salary data, using our attacks, we can predict salaries to within 2% median error using only 50 range queries. The other way we use these ideas from learning theory is to present the first fully generic results on database reconstruction. That is, these results hold for any query class and don't assume anything additional about the query class, like it's a specific one like k-nearest neighbors or range queries. Our first generic result is a reduction from database reconstruction in the setting where the adversary has some known queries to pack learning. What this result says, essentially, is that pack learning can be used generically as a database reconstruction attack. Our next generic result is a minimal attack that holds for any query class based on ideas from epsilon nets. We instantiate this attack with the first reconstruction for prefix queries. Finally, using this connection to epsilon nets, we turn the attack around to prove the first general lower bound on the number of queries needed for database reconstruction for any class of queries. And this lower bound is interesting. Aside from it being the first lower bound, a fully general lower bound proven, it shows that the VC dimension of the class of queries, which I'll talk about a little bit later, is related to how damaging the access pattern leakage from that query class is. So because time is so short, I won't have time to talk about the generic attacks in this talk, but I urge you to read the paper if you're curious. Instead, I'll try to give you a flavor of the new database reconstruction attached for range queries and how they use learning theory. Before discussing these attacks, we'll review some notation and terminology. Throughout the talk, we'll use n to refer to the number of possible values a database record can take on. A range query is an interval of numbers between 1 and n, so kind of the sub-interval of the numbers 1 through n. We abstract the database as a collection of records, each containing some value between 1 and n. So let's look at this example database. It has 4 records. With the range query 710, the records with values 8 and 9 are returned. And these records have identifiers 2 and 4. The adversary's view of this interaction is what the access pattern leakage is. It's just the identifiers of the matching records. And throughout this talk, we'll assume that that's the only leakage available to the adversary. And importantly, these identifiers are stable over time, so the adversary can tell when 2 queries return the same record. Given only the access pattern leakage, a full database reconstruction attack recovers every value in the database exactly. To within an approximate database reconstruction attack recovers all values to within some additive epsilon error. So for example, epsilon equals 0.05 is recovery within 5%. And epsilon equals 1 over n is full database reconstruction. And finally, we'll call an attack scale-free if its query complexity is independent of the number of records or the size of the domain. This work presents 3 database reconstruction attacks for access pattern leakage from range queries. All of these attacks are scale-free. The first is a direct generalization of the techniques of Kellaris et al. And achieves approximate database reconstruction for any database with 1 over epsilon to the 4 log 1 over epsilon uniformly random range queries. Taking epsilon to be 1 over n, we recover the KKNO's attack query complexity exactly. We also show a big omega of 1 over epsilon to the 4th lower bound for this goal. Next, under a very mild assumption about the database, we show that a new attack, approx value, that achieves approximate database reconstruction in 1 over epsilon squared log 1 over epsilon queries. Again, this implies we're setting epsilon to be 1 over n, an attack, a full database reconstruction attack that works in n squared log n queries. We show a matching lower bound for this goal as well. Last, we show the approximate order attack. This attack is somewhat different than the first 2. Its goal is approximate order reconstruction, or revealing the order of pairs of records in the database, except for pairs whose values are less than epsilon apart. In the paper, we show that with a distribution on the database, you can use approximate order reconstruction to get approximate database reconstruction. Additionally, because if the database is dense, approximate order reconstruction immediately implies database reconstruction, this attack implies a result equivalent to Lacharité et al.'s main attack from Oakland last year. And in this talk, I won't talk too much about the exact success condition, but to get around a lower bound from Lacharité et al. Last year, we do have to mildly relax the success condition we expect. See the paper for more details if you're curious about this. So our starting point is the same as the Kellaris et al. Attack for the generalized KKNO, our generalized KKNO attack. We assume a uniform distribution over the range queries. Thus, each of the n times n plus 1 over 2 possible range queries is chosen with equal probability. This query distribution induces a distribution over the values, namely the probability that a query accesses that value. For value I, this is computed as the sum of probabilities of all ranges containing I. This distribution has a closed form expression which isn't too terribly important for this talk. But it's quadratic, concave down, and attains its maximum at the midpoint n over 2. Values near the endpoints are much less probable than values near the middle. The basic tool of this attack is at what was used in Kellaris et al., which is to estimate each record's probability under this distribution f from the access pattern leakage. For each record, we're first going to count the number of times it's returned by a query and divide by the total number of queries. This gives an estimate of f of value for each record, so a point on the y-axis. Then the second step of the attack uncovers the value by inverting the function and finding the value on the x-axis with that y-axis value. So we see one problem with this right away. This function is such that there are 2 values on the x-axis for every y-axis value. So this is the question of symmetry. So to recover values in the database, we need to break this symmetry. And this is possible, but the details aren't too interesting, so I'll just defer you to the paper for details. So then with this, the question becomes, how many queries do we need to get an accurate enough estimate of the value of f for each of the records in the database to accomplish epsilon approximate database reconstruction? And to understand this, we'll take a quick detour into probability. Imagine that you have a set X on which there's a probability distribution D, and let C be a subset of X. The task we want to do is to estimate the probability of the set from taking samples from D. So we take some samples, and we estimate the probability by dividing the number of samples in the set by the number of total samples. So for this set C, the estimate of the probability would be 3/7. So the sample complexity of doing this for a single set is, to measure the probability of the set within epsilon, is big O of 1/epsilon squared by a Chernoff bound. Now imagine that instead of a single set, you have a collection of sets, and you want to estimate the probability of all sets simultaneously. We'll still compute the estimate for each set the same way. What we want is that the estimate for every set in C is at most epsilon away from its true probability. A set of samples with this property is called an epsilon sample for the collection of sets C. Now we come to the question, how many samples of D do we need to get an epsilon sample for C with high probability? One way to analyze this is to take a union bound over each set in C, but this bound incurs a cost that depends on the size of the set. However, Vapnik and Chervenankis proved in 1971 that if the set C has VC dimension D, the sample complexity of an epsilon sample is only big O of D/epsilon squared log D/epsilon. I won't try to explain VC dimension in this talk. It takes a little bit of time to get your head wrapped around it. But you can think of it as just a small constant for the purposes of this talk. So this result is very surprising because it implies that you can estimate the probabilities of all of these sets together with a number of samples that doesn't depend on the number of sets at all. So this will be very useful for building scale-free attacks. So we can apply this nice theorem pretty much directly to analyze the query complexity of this generalized KKNO attack. We just need to define the sets X and C. So for X, we'll take the set of all range queries on 1 through n. And for C, we'll define for each value in 1 through n a set for the range queries that contain that value. The VC dimension of this set is 2. So by applying the epsilon sample theorem, we get that the query complexity is epsilon to the 4 log epsilon. The epsilon to the 4, distinct from the epsilon squared in the theorem, is because we need to invert the function f, which is quadratic. So we actually need to get error proportional to epsilon squared instead of just epsilon. So you get a square and then you square again to get the full sample complexity. So because this fourth power exponent is a little bit intimidating, a natural question is, can we get rid of this squaring? So that's the hypothesis that we need to make for the next attack. So assume that there exists at least one record in the interval n/8 to 3n/8. And the exact numbers here aren't too important, but we just need to assume that there's at least one record, at least more than a constant, away from the endpoint or the middle. And so with this minor assumption, the approximate value attack recovers values with only epsilon to the -2 log epsilon inverse queries. So with that, I'll conclude. I'd like to thank everybody for listening and take any questions.
Just state your name when you ask a question.
Sure. Ellie Canal, Software Engineering Institute, CMU. Interesting talk, and I apologize if you said this, I missed it. Are there any assumptions on the distribution of the points within the sets, or is it a uniform assumption?
Which sets, I'm sorry?
So I have this overall search space, and I'm trying to construct these smaller sets within the search space. Is there an assumption about how the points are distributed? Can they all be clumped at one end? Do they assume to be, are all the points?
Oh, no. So the generalized KKNO attack doesn't make any assumptions. And the approximate value attack makes a very mild assumption that there's kind of one point that's not kind of at the very extreme ends of the database.
So I'm just trying to think intuitively about it. If I have a database which has a significant clustering of points in a single area, and then there's a large sparse area, I guess, so part of the range, that theoretically the same attack should function.
Mm-hmm.
Cool, thank you.
Hi, Ling Ren from VMware Research. So what mitigations would you recommend?
That's a good question. The question of mitigations is pretty tough, and I don't know that there are necessarily good kind of like silver bullet solutions for mitigating attacks on access pattern leakage. I've thought about this a little bit, and I think the best mitigation for building a practical system, it might just be bucketization. So instead of allowing arbitrary range queries, you kind of bucketize the values and only allow range queries that access kind of their prefixes. So you don't, you basically treat like values that are close together as being the same value for the purpose of the range query. And this seems like it might be the only way to kind of make a very strong generic argument that data can't be leaked from range queries. Basically because the low order bits are independent of the access pattern leakage, and if you bucketize. So.
Ray Schuster, Tel Aviv University and Cornell Tech. Could you elaborate a little bit about what's hiding in the big O notation?
That's a very good question. So the VC theorem is notoriously loose in the constants. I think the proven constants from their original paper might be as high as 64 or 128 or something like that. So we actually did implement the approx value attack and did some simulations, and we showed that the effective constants, at least in our simulations, are only about 1. So if you take what's inside the big O notation and just plot that versus then what the simulation gives you, it looks like that just epsilon squared log epsilon is, predictive of how the attack behaves in terms of query complexity. So the effective constants are very low.
So I'm trying to decide whether encrypted databases are totally dead or just fragile. And one of the assumptions you made in the paper was uniform queries, and in fact that has to come into your attack very critically in the VC dimension. So if A, your queries are not uniform, if they're actually coming from a real-world distribution, does that help? And B, why is the notion of full reconstruction the goal? I mean, it seems like if I have an encrypted database and after making like a local set of queries around a local spot, if I'm able to deduce just from the access pattern something about that, I would consider that a break. So why is the bar full reconstruction instead of local attack?
Well, so the full reconstruction refers to recovering every value exactly.
Right.
And so what we target in this work is approximate reconstruction, which is recovering every value approximately. And so what you're saying is essentially, why don't we weaken the goal further and say, what if you can only recover some values well approximately? I think the reason why people haven't studied that as an attack goal yet is because it's a little hard to reason about formally, because you have to think about like, okay, like at what point does an attack succeed or fail, or at which points do we care about recovering, and how granular recovery do you want? But certainly I think that recovering some points well is an interesting thing to study in further work. As to your broader question about whether encrypted databases are completely toast, I think that while it's clear that access pattern leakage is very damaging, I don't think it's necessarily safe to conclude that this breaks encrypted databases completely, because it's true that the access pattern leakage from very few queries doesn't leak very much information. And in fact, we show our last generic result in this paper is actually a lower bound on the on the kind of reconstruction accuracy of any attack that shows a trade-off between the reconstruction accuracy and the query complexity of the attack. So we do know that there are some limits on what can be reconstructed given few queries. So this to me motivates restrictions of the threat model. So it seems like these efficient systems can't be provably secure in the setting where the adversary has very many queries, but it still seems like we can make strong security statements about settings where the adversary only has a few queries, like a snapshot attack, for example. And it seems like this is a real attack where encrypted databases do provide a strong security guarantee. So I think we can't necessarily achieve the dream of getting persistent, strong provable security with persistent adversaries without using ORAM or anything like that. But we can still design systems that have good provable guarantees, and that these guarantees are kind of meaningful in practice as well.
I think we're out of time, so let's thank the speaker. You can follow up after. Paul will be here.